We turn now to single molecule force spectroscopy. So the AFM is of course capable of measuring forces of interaction with a single molecule. This slide shows the pulling apart of a polyprotein. So this is a protein that consists of folded domains connected together in one long chain. What you're looking at here is a force distance curve turned upside down. So if we normally think of the adhesion causing a retraction curve to look like this, here the curve is turned upside down so that it looks like this. So the sign of force is changed in these plots, and what we're looking at is as you pull on the end of the polyprotein with the AFM probe, one of these domains will stretch, in fact they'll all stretch, but then suddenly one will unwind to give an increase in length so that one now sees the probe moved out over here, and then you'll stretch the next domain and it will unwind and so on. This is one type of single molecule force spectroscopy measurement. Another type comes by attaching a flexible tether to the probe so that the probe doesn't interact with the surface too strongly and a molecule of interest, and putting on the surface another molecule that binds the first molecule, and then making a measurement much like this, in which case one, again, plotting force the same way, sees the force increasing and then dropping down to zero as the bond breaks. So the description of the process is similar in both cases. The nice thing about the polyprotein measurement is the repeated nature of these curves here is good evidence that one is pulling one domain to pieces at a time, and by using different types of polyprotein one can verify this. So what's going on at the level of molecular interactions? So imagine here that we have some energy landscape in which this is the equilibrium state of either a folded protein or one protein, for example, binding a receptor on the surface down here. If we pull on it, we know that it won't spontaneously dissociate or fall to pieces. Like any chemical bond or a folded system in the presence of thermal noise, there's a transition state for the system to come to pieces, and this is represented by a barrier here that we have called ETS. Now in the case of unfolding a protein or breaking a bond like this, there's no bound state out here, so the energy is just simply constant and somewhat higher for the unfolded or dissociated state. Now if we apply a force to this system, we add extra free energy to the system. So this is, if you like, distance along here, along the unfolding path, and if we apply a force in that direction, we add an extra free energy equal to force times distance. And so that is plotted by this dashed curve here. And when we sum the two forces or the two energies together, we end up with a sloped curve something like this. The result is that the height of this transition state is reduced relative to the equilibrium state here, and the system dissociates more frequently. I've plotted on this graph these parameters, the length of the bound state at 1 kT above the minimum, the width of the saddle point at 1 kT below the maximum, and then this distance from the minimum to the maximum as the distance to the transition state for a reason, because this next slide shows what's going on. We can, using Cramers theory, describe the off rate in a potential like this according to this prefactor here, which is given in these variables. This was discussed in chapter 3, LTS, times the exponential of minus ETS on KT. So this is the off rate for the system. When we slope it and add this extra free energy, the force times the distance to the transition state, we then increase the off rate by decreasing this barrier to dissociation. In an AFM experiment, the dissociation is a little more complicated. The reason for this is that as we pull the probe away from a surface, so let's imagine we have some bound state here and some flexible tether that we are now stretching as we pull away from the surface, we increase the force on this system linearly at a rate that is given by this spring constant times the velocity of the probe. So this system is being loaded at some rate RF newtons per second. In that situation, one can solve for the most probable breaking force of the bond, or unfolding force of the protein, to get this formula you see on the left here. So if one then plots the distribution of unbinding forces against the number of events against the unbinding force, it's probabilistic, and so one has some distribution. Solving for this most probable unbinding force and plotting this against the log of the loading rate, one gets a straight line plot of this sort for one unfolding process. From the function in the middle of the slide here, one can see then that the off rate and the distance to the transition state can be deduced in the following way. The slope of this curve here gives the following quantity, where x is the distance to the transition state, and the intercept gives this somewhat more complicated quantity, so that knowing the distance to the transition state, the off rate can be deduced, albeit with considerable uncertainty.